So there's a mix of epidemiologists and statisticians. The other question I would like to ask just to start is I want to get a little bit how much mediation analysis some of you already know. So for example, who knows what's the difference between a controlled direct effect and a natural direct effect? That means, yeah, okay, that's, I guess, for that half, then maybe the beginning will be a little bit slow, I guess, because not everybody has that foundation. Maybe I will start as I planned from the beginning. So actually, it'd be good if I could get rid of this, wouldn't it? So that's not. If I move up, that's better, isn't it? The plan is that I'll start with called setting the scene. So I'll talk for probably of an hour to an hour, giving introduction to the sort of basic themes, mediation analysis. I know maybe not all of you are interested in seeing all the details, all the maths, and there is some maths to come, but I think the emphasis I try to give is not on understanding every single part, every single equation, but sometimes I'll use the equations to get across a general idea. So it's really all focused on the mathematical side. And then a short break for coffee, etc., and then come back, and there'll be a chance for you to analyze the data that sort of forms the case study for this first workshop. And so that will probably take us another hour or so, and then we'll have the some of the questions and answers with issues that arise from what you've done on the case study. So that's my sort of general plan for the afternoon. We'll have to be flexible and see how it goes. But please ask questions as we go along, because you know, especially when there's a mixed group like this, that I don't know you and you don't know me, and not everybody knows each other, it's very likely that I'll use words that somebody doesn't understand, and please ask when that is the case. If I'm going too fast or I'm going too slow, you know, however you can good luck as we go along. Please do that, and so that it can be as interactive as possible. For nearly a century, statisticians and researchers in many different fields have been attempting to address questions that we would broadly call questions concerning mediation. So for example, in today's case study, the question of interest, if you like, is about the effect of alcohol intake on systolic blood pressure. So we know that drinking more seems to have an effect of raising your blood pressure, your systolic blood pressure. The biological mechanism through which this takes place is not well understood. And one theory that has been proposed is that perhaps the enzyme glutamyl transpeptidase, or we'll call it GGT, sometimes called GGT, I think this enzyme gamma GT could play a role in explaining some of that effect. So as it might be that, well, I think it's well established that drinking will raise your gamma GT, but the theory is that perhaps it's that elevated GGT that then goes on to lead to elevated blood pressure. One sort of proposed mechanism through which this effect of alcohol intake on systolic blood pressure might be acting. This is a typical mediation question where people want to know, so is there a pathway, as suggested here, through GGT? Is there such a pathway at all? And then if there is, how important is it? So in other words, how much of the effect of alcohol on the blood pressure is via GGT? This is one example out of millions you could think of questions, scientific questions in many different fields basically our questions of mediation. It's not always stated as such, but I think many things that ask are of this form. So I was talking to someone the other day who had found that in perinatal intensive care units, girls higher mortality than boys. And she was trying to say, will my confounders explain this? But then I thought, she doesn't really have confounders, she has mediators, because nothing causes sex. So really sex is her exposure. And she's noticing that there is an effect of sex on mortality. And then she wants to know what are the things along the way that are explaining this effect. So really it was a question of mediation, even though she didn't phrase it perhaps exactly as such. One thing I should say already is when we're talking about these sort of biological examples, you know, whether drinking affects systolic blood pressure via something like GGT, then really things are naturally more complicated, aren't they? Because an individual's alcohol intake is changing over time, their GT is changing over time, their systolic blood pressure is changing over time. So even if this mediation is actually happening, it's really happening in this picture. I don't know, no, it doesn't see a way of my moving that green, I'm afraid, so that would always be hovering there, sorry. So underneath that it says, of course, things are rarely this simple. So even you could say this second picture is sort of making things look discrete that are really continuous. So your systolic blood pressure is a continuously changing process. The work on mediation analysis has been criticised, and rightly so, I would say, by Odd Orton and the group of authors. They were pointing out that when people, even if it is the case that biologically this affects another entirely via some mediating process, if you only have one measurement of this, one measurement of that, and one measurement of the mediator, then you never fully capture that full mediation of processes that are going on. So when we are talking about snapshots, actually single snapshots like this one, then we should be aware that probably what we will be estimating is only part of this more complex picture. And in a very recent paper, Tyler van der Wiel, who has done much of the work in this area, he and Chetkin have a nice paper on extending mediation analysis precisely to this setting where you have a time-changing exposure and a time-changing mediator. So we're going to talk about that today, but I'm saying if it worries you that we're talking about this example in this slightly simplistic way, I'm just making the point that that limitation has been acknowledged and indeed something has been done about it. But now we'll just pretend that alcohol intake doesn't change that much over the lifetime. GGT is relatively constant, SB is relatively constant, so that it somehow makes sense to talk about this median problem using the snapshot variables. Okay, so as I said initially, this has been done, and I dare say that most of you have, all of you, have done some mediation analysis, even the ones who didn't put their hands up about knowing about controlled and natural direct effects and so on. I'm sure that almost all of us at some point in our lives have done what we would call traditional mediation analysis. And what I mean by traditional mediation analysis is that you fit, and epidemiologists usually do, is to fit a model for the outcome given the exposure and maybe some confounders, and add the mediator into that model. We look at the coefficient of the exposure and see how it changes. The law being that if the exposure effect goes away when you adjust for the mediator, then it's completely mediated through that variable. Whereas nothing much happens when you add the mediator in, then mediator is not a mediator at all, and all the continuum of possibilities in between, where things are partially mediated. So that's a traditional approach, and in the social sciences, it was framed as in an equivalent way, but instead of fitting two models for the outcome with and without the mediator and seeing what happens, exposure effect, the scientists tend to think about it this way. So first of all, they attempted only using linear models, and then two models are fitted. First of all, a model for m given x, so a linear regression model for m given x, and then a second linear regression model for y given x and m. And so then the coefficient of x in this second model, so this is the model where you include the mediator, so the coefficient of x is then labeled the direct effect because it's sort of the effect where you've blocked the, so you've just got the part, so that it makes some sense to think of B1 as a direct effect of my not via m, and alpha 1 times beta 2 as the direct effect. So linear regression models are simple as this. This makes sense that this alpha 1 times beta 2. So alpha 1 is the change in the expectation of m that you would expect to see to change x by 1 unit. And so you translate that change in m multiplied by beta 2 is then the change that you would expect to see in y for a unit change in x, the part that is transmitted by m. You see that there is some sense in multiplying those coefficients in a linear model. So sort of this way of doing traditional mediation analysis is sometimes called the product rule. So alpha 1 times beta 2, this multiplying coefficients along paths is called path tracing or product method. The epidemiologists often do is the difference method, where you don't fit this model for the mediator, but you fit this model for the outcome, and then you fit a second model for the outcome, but during m, so you have expression of y given x equals, let's say, gamma 0 plus gamma 1 x. Beta 1 is still your direct effect, and your indirect effect then becomes gamma, the coefficient in this model with m, minus beta 1. And that's sometimes called the difference method. And gamma 1 minus beta 1 is equal to alpha 1 times beta 2. So the two things are completely equivalent. It's a simple situation where everything is linear. But in a sense, it only exists in the simple setting where everything is linear. So in the setting where these two things exist, they are identical. So the difference method is often said. So I've just focused on the product method, but the difference method is the same. And of course, the advantage of thinking in terms of the product method rather than the difference method is that when you go to more complex diagrams, that product method, it's not going to make sense to do the, well, I mean, you could do the difference method in order to get, you know, the direct effect and the indirect effect, two of them together. But if you want to start thinking about a particular pathway, like let's say this red pathway here, then the product method extends to this. So you fit a linear regression model for m1 given x, another one for m2 given x, one for m3 given m1, one for m4 given m1 given and then m2, then 5 given m4, and so forth. So you keep fitting the regression models at every point in the diagram. And the coefficient then corresponding to each red arrow would just be multiplied together, and that would be your estimate of that, along that path. So again, it's well if everything is a linear regression model. But who lives in a world where every variable is continuous and every model is linear, and there's never an interaction or a squared term or everything is really as simple as that? I think it's very unlikely, and especially, and maybe this is why the social scientists have used this approach more, because they often have scales, don't they? Scores on tests and scales, and whereas in epidemiology there are often binary variables. Do you have this disease or not, and so forth. So really, this all falls apart once you have some binary variables in there. And of course, have tried to use regardless. So what they'll do is, let's say M4 is binary, then fit a logistic regression model for M4 given M1 and M2. Log odds ratio that corresponds to the effect of M1 in that model would think that they multiply with all the other linear regression coefficients. But now has no basis in statistical theory, or there is no rationale for doing it. Why are you multiplying a log odds ratio with a linear regression coefficient? It means it doesn't really mean anything anymore. Okay, so it's not surprising that the causal inference got involved, because here was something that seemed obviously a causal concept, right? Because associations are symmetric. If it is associated with Y, then Y is associated with X. But as soon as you're talking about mediation, you're applying some ordered sequence. If something comes in between X and Y, then it can no longer be the case that it's symmetry. Because if M comes in between X and Y, then to say the effect of X on Y is mediated by M, you're really obviously talking about something that mind is causal, whether it's explicitly so or not. So, I think what are the core principles of these modern causal inference methods? Well, core principles are first to ask, what is yes demand? What are we actually trying to do here? With direct and indirect effects. If they're intuitive, I think, I think we share some understanding of what it means that X affects Y via M, but do we have a precise meaning for that concept of direct and indirect effects and mediation? Sort of starting point when Greenland first got in 1992, they started saying, okay, lots of people are doing this mediation analysis, but is it that they're actually after? What are the effects of interest? So what is the S demand? What are the S demands of interest? And of course, in this different school of thinking, once you've established what it is you're trying to estimate, you then ask, under what assumptions can you do? Under what assumptions can this effect be identified from the data? And the question is, are there better estimation methods than those currently used? And so setting already said that the estimation methods are very limited, because this whole way of thinking only works when you've got linear regression models, simple linear regression models everywhere with no interaction. So it means that, if you're prepared to say, well, I'm not that bothered about 1 and 2, it's fine to be a little bit vague about these things, then those people who don't mind vagueness would find the limitation of linear regression overwhelming. So there is interest even, I think, from those who are keen on causal inference, because they feel it's too pathetic. I think even those people still feel that mediation analysis, causal mediation analysis, has something to offer if able to relax number 3. Okay. Always when the causal inference school tries to precise some causal concepts, it tends to use counterfactuals or potential outcomes. Of course, it's the only way, and there are alternatives, and those alternatives have been used. If you read works of Vanessa Deleuze and Sarah Geneletti, etc., they have done. They've established these concepts without potential outcomes or counterfactuals, but you could say there's always an equivalence of some sort between the two. So today, because potential outcomes and counterfactuals that are more commonly used, I will stick to counterfactuals or potential outcomes and mediators. So we'll write Y, capital Y, with a less in brackets to mean the values of counterfactual, the potential outcome Y, the value that Y would take if we intervened on capital X and so it's possibly counterfact to the value little x. So these are hypothetical interventions. It doesn't mean that we have some intervention, some practical intervention in mind, but just way of conceptualizing causal effects. So if we could somehow set x to little x, then yx would be the resulting value. So that's a concept that you would have met in other fields of causal inference. But now, because we're talking about mediation analysis, we'll also talk about yxm, the value that y would take if we intervened on both x and m, the exposure and the mediator, and then to the value little x and little m. And then we have mx, the value that m would take if we intervene on x and set it to little x. Now, what we're looking to have is this more difficult looking quantity, x, mx star, the value that y would hypothetically take if we hypothetically intervene on the exposure and set it to some value, let's call it little x, while simultaneously intervening on the mediator and setting it to the value that m would have taken x being set to x star. Repeat that. So we're thinking we have a thought experiment, and it's very much just a thought experiment, not a practical experiment. So in our case of alcohol as x, GG as m, and blood pressure as y, we're saying what would the systolic blood pressure of this person be if we could make him drink, so x equal to 1, but set his GGT to be the level that it would have been had he not drunk, x star equal to 0. So that's an example of y1 m0 I've given there. But the idea of y1 m1, and that's what would SBP, what would the blood pressure be of this person if we make him drink, but also make his GGT be the value that would have been had he been a drinker. It's the same as saying, so we use the 10 for a moment. So for binary exposure x, this y x m x really has 4 for a binary x. This can be 0 or 1 and x is less. It can be 0 or 1, so we really have y1 m1, y1 m0, y0 m1, and y0 m0. What I'm saying is that it's packed. This is just y1, and this is just y0. Does that seem right to you? So when you say, what would your systolic blood pressure be if we pick your drinking status to non-drinking and pick your GGT to what it would have been had you not been a drinker? That's exactly the same as just saying, well, I'm picking your, I'm picking x to be 0, and then I'm letting m follow from that. So that's just what we mean by picking x to 0. It's these in the middle that are the difficult ones. What your blood pressure would be if you drink, but make your GGT look as if you had not been a drinker. Or what would happen to your blood pressure if we made not a drinker, but made your GGT be the value that it would have been had you been a drinker. You see that these are sometimes called nested counterfactuals, because there's counterfactual within another. And it's a sort of particularly problematic thing, because, counterfactuals or potential outcomes are already hypothetical quantities, but these nested counterfactuals are sort of doubly hypothetical, because these, when we talk about what would your systolic blood pressure have been had you been a drinker, then maybe we can't see that because you're not a drinker, but we just imagine a hypothetical experiment where we make you a drinker. But in a hypothetical experiment where these counterfactuals could be observed, because you're simultaneously having to put someone in 2 levels of the exposure at once. You can have written about where you set x to 0 and you observe m, and then you go back to the beginning and you set x again to 1, and then set m to what the m turned out to be in the previous experiment. But once repeating the experiment, it's not really the same thing anymore. So lots of sort of philosophical debate about these net counterfactuals and whether they're things to be discussing or not. But in any case, they what we use to create these model-free definitions, these precise definitions of direct and indirect effects. That's better than just what we have so far from the traditional mediation analysis was, well, beta 1 in this model, but beta 1 is just a parameter in a model. We want what is the real concept of direct and indirect effects. And counterfactuals, these potential outcomes, have been used to make that clear. So let's now get on to those. So the controlled direct effect, x on y, m is controlled at little m, and the marginal mean difference is this thing here. So one caveat, it's difficult to know how many sides to say, because you sort of end up disrupting the flow by interjecting with so many sides. But on the other hand, if I don't do that, I fear that often people walk away with the idea that if they're going to do any sort of causal inference at all, they have to be interested in differences of means. It's always the case that we start off with the example of the difference of two means. But of course, you can equally form the ratio of two means or the ratio of two odds. I mean, there is nothing, and indeed in the survival literature on mediation, all the effects exist as hazard ratios and hazard differences and accelerated failure time models and so forth. So there is really no restriction to mean differences, and no restriction either in looking at marginal mean differences. So here I've written this controlled direct effect as the expectation of something minus the expectation of something else. But traditional epidemiology, people are used to interpreting conditional effects, aren't they? They fit a logistic regression model and they have lots of covariates in that model, and then the effect is conditional on that. And there is nothing wrong with that. So if you're interested in an effect that is conditional on gender, for example, then you can define your effect of interest as the expectation of y given gender minus the expectation of y0, m given gender. So I just want to make sure that nobody with this false impression that while you're doing things this way, you have to be interested in marginal mean differences. That is not the case. However, just for simplicity, I'll now stick to only talking about marginal mean differences. This controlled direct effect is defined like this. And as always, almost always, even as always, with a causal contrast, it's a comparison of two hypothetical situations. So we have the expression of y under one hypothetical situation, that in which you set x to 1 and set m to little m, and here's the expectation of y under a different hypothetical situation. You set x to 0 and set m to little m. So because in the first situation you're setting x to 1, and in the second you're setting x to 0, so x changes between the two situations, but m stays the same in the two situations, so you're setting m to little m in both situations. So you see that this effectively matches some idea, at least, of a direct effect, because we're setting m at little m and then changing x from 1 to 0. So we see an effect. If this controlled direct effect is non-zero, then it must be that there is some effect of x on y that is not via m. I'm not talking yet about how we estimate these things, just how we define them first. So in our example, this is the change in systolic blood pressure. Everyone versus no one drinks, with one having their GGT fixed to a common value, little m. So in the case study, analyze in a moment, I ask you to fix log GGT to 3, in fact. So the GGT will be fixed to e to the 3, because that's just a sort of normal value of GGT. But there is obviously a question once you're talking about control direct effects. Well, there's not just one, because there could be as there are different values of m. So once you choose a particular value of GGT, it seems a bit strange. And indeed, these two hypothetical situations are strange. Because you're thinking about comparing making one drink versus making no one drink, and setting everybody's GGT to precisely the same value. And that's because we know that there is naturally this distribution of values of GGT. It seems odd to imagine a world where everybody's GGT is exactly the same. But that's how the control direct effect is defined. Now, a different notion of a direct effect, known as a natural direct effect, expressed as a marginal mean difference. See these fringe potential outcomes coming in. Precisely this one is now in. So the difference between this and this, the difference of the expectation of those two things, the natural direct effect. So again, it's a comparison of two hypothetical situations. Again, x is set to 1 and then to 0. But both situations now, instead of being set to some fixed value m, is set to m0, the value that it would be had x been 0. So no longer the case that we're imagining a world where everybody has the same GGT. But if we imagine that the patient of interest is everybody in this room, and we all have, the idea, at least hypothetically, is that we each have 2 levels of GGT, the one that we would have had we been a drinker, and the one we would have had we been a non-drinker, and one of those we get to see. So if you imagine our level of GGT exposure, no drinking, that still varies from person to person. M0 is different from person to person, and yet in this comparison of two situations, whatever your M0 is, goes in here and it goes in here. So the same, if you like, within subject in this comparison. So in the two situations, each subject has their M fixed to the same thing. So we're intuitively getting at some sort of direct effect, because if this is 0, there must be an effect of X on Y that is not via M, because this was not going to capture any of the effect that's via M, because M has been set to M0 in both halves of the expression. So next question, so when we talk about direct effects, we're not really clear whether we mean control direct effect or natural direct effect, or indeed perhaps other nodes of direct effect. So the thing is that if there is no individual level interaction between X and M, so if setting X to 1 has the effect on Y for each person individually, irrespective of what you set their M to, then you'll see that the control direct effect will be the same at every value of M, and that will be the same as the natural direct effect. And we're basically saying, if it doesn't matter for any individual, this difference between these two counterfactuals is the same no matter what you put in this second entry. Then obviously the control direct effect is the same and will be the same as the natural direct effect. But if that's not the case, then in general there could always be a difference between the direct effects with each other and the difference between those and the natural direct. Yes.
So if that's the case, that means there's no mediation by N. If it doesn't matter what N is, that doesn't matter.
No, I think there could still be. What we're saying is for each person I, it's different, isn't it? So, I guess, two different values of all. It's possible. I mean, I don't think it's possible for a binary outcome, because binary outcome, if this difference is always the same, then it's either always zero or I mean, there's something strange going on with, for a binary outcome, contrast can never be the same for everybody, unless you're in some very extreme situation where X has to be determined Y, in which case there is a but you it for a continuous outcome like blood pressure, then it's extremely implausible, but it is just about possible that X drinking, let's say, increases your blood pressure. So if you take X, the remaining X of X on Y is to raise blood pressure by 22 units. And that could be the case no matter what level you set M. And this is the case. Yes, so it doesn't need to be the same difference for every I. So scrap that. It doesn't be the same for each person, but this difference, this difference needs to be the same difference for each person, for each value of M1 and M2. So for you, 2 for me is 93. But no matter what we set our EDT to, the residual for you will always be 2, and for me will always be 3. Then it could be that X of M and M of X Y. So for example, you could have, if you wanted to, you would say you drop X from a Bernoulli distribution with mean half, you draw M from a normal distribution with mean X, let's say, variance 1, and then you draw Y from a normal distribution with mean X plus M and variance 1. That situation where there's no interaction between X and M, but there is still both a direct and an indirect effect. So there's a direct effect of 1, and there's an indirect effect of 1. That's the situation where the control direct effect will be 1 for every value of M, and the natural direct effect will be 1. But in fact, direct effect will also be 1. So I don't think, so this is not that there's no mediation. I think that if you have no individual level interaction between X and M, then control direct effects will be the same, and those control direct effects will be equal to the natural direct effect, but equal to the total effect. So there could still be mediation.
How about the level behind which natural direct effect? How about M1? M1 is M1 is 2.
So that's a very good point.
Yeah.
So it is arbitrary that this is in fact find the natural direct effect to be the difference between Y1 M0 and Y0 M0. And you're saying Y is instead to the expectation of Y1 M1 Y0 M1. So that still capture the same sort of idea with it. You set M1 to the same thing here, set into the same thing here and here, and you change X. So indeed, so this sometimes is called the pure natural direct effect, and this is sometimes called the this is good observation. There is no particular reason, in particular examples there could be, but there is no reason in general to think that this is more interesting than the other one. So we'll get to that in a moment because it's relevant to this next slide. So now that you have a natural direct effect, there is also a natural indirect effect, which is written like this. So then the difference between two hypothetical situations. So now we're changing m from m1 to m0 while setting x at 1. The equivalent question now would be why set x at 1 and not at 0? So we'll come to that in a moment. But it seems sensible to define indirect effect this way because x is allowed to influence y only through its influence on m. That's kind of what we're saying here, isn't it? This difference captures the effect of x on y that is transmitted by m, because the only thing that changes is that you change your m from m0 to m1. Do you intuitively that captures the effect of x on y that's via m?
And when m is equal to just the 1, or is m equal to the fraction of 1? So is that notation?
This m1 is the hypothetical value that m would take if x was set to value 1. So in our example of GGT, everybody in the room has two GGTs, hypothetically. They have their GGT and the no drinking and their GGT and the drinking. This is your hypothetical GGT and the drinking, and this is your hypothetical GGT and the no drinking. Whereas we just had little m in our definition of a controlled direct effect, little m is just a value of GGT, like 3, that we just choose 3 for everybody. The difference is that a less value, a lowercase letter, I will always use to denote just a typical, a possible value of that random variable. But it's fixed, so it's like m would be 0, or 1, or 2, or 3, whatever. Whereas our random variables, these m1s and m0s are random variables, they're not the same for everybody in the room. The person has an m0 and an m1, they're counterfactors, they're potential mediators. The potential value of the mediator were x set to 1 or 0. Natural indirect effect you can think of as the change in mean SBP we would see, change everyone's GGT from its non-drinking level to its drinking level while fixing the exposure to drinking. So sometimes some people also talk about that effect, this natural direct effect, as it's like of x on y were x not to have an effect on m. Effect of x on y via its effect on m. Why do we choose the 1s here rather than the 0s? The 0s here rather than the 1s. So it's for this reason. So for better or worse, the sort of aim of the people have when they do mediation analysis is they want to decompose the total effect into a direct part and an indirect part. We can talk how important this mediator is. If almost all of the effect of drinking on alcohol is this indirect effect via GGT, of alcohol on blood pressure, is this indirect effect via GGT, we know it's an important mediator. And that is, even if we can't intervene on drinking, we can try to intervene on GGT. It's that sort of thinking that often accompanies this kind of analysis. So the idea of decomposing the total effect into a direct part and an indirect part. And here, I've written again the natural direct effect, and and here written again the natural indirect effect, and see that these two bits red cancel out, and so you're left with ym expectation of y1 m1 minus expectation of y0 m0. And as we already said, this is the expectation of y1 minus expectation of y0. In other words, the total effect of x on y. And so you see that it was important that we chose there and 1 there to make these two things cancel out. But if we had made the other choice, so we have, I said, natural indirect effect is equal to the expectation of y1 m1 minus y1 m0. Because when we added this, the things cancel, and we have with y1 minus y0. This is actually called the total natural indirect effect. The pure natural indirect effect, which is the expectation of y0 m1 minus y0 m0. So that's exactly the same, but now making the other choice. Instead of fixing x to 1, we fix x to 0. And these two adds to give the total. So 2 choices for the direct effect, 2 choices for the indirect effect. And this plus this gives us the total effect, and this plus this gives us the total effect. But this doesn't, and this plus this doesn't. So 2 choices for the natural direct effect, 2 choices for the natural indirect effect, and then there are 4 possible sums could make, but only 2 of them make the total. So really there are 2 ways of decomposing the total effect into an indirect effect. Either you do it this way, or you do it this way. So those 2 ways differ. Obviously, if there's no interaction at all between x and m, the null and the full and total natural the effects are the same, these 2 things are the same, and these 2 things are the same. So, in a very nice paper a few years ago, Tyler and Daniel showed that really the total of an effect can be written as the pure natural direct effect, the pure natural indirect effect, plus something else. Because we've already said that if you just add these 2, you don't get the total. If you add these 2, you get something. The total causative effect starts from some remainder term. And in that case, it shows that this remainder term is the mediated interaction. So it's the effect of x on y that is, so it's, I think, this mediated interaction. If the term is only non-zero if there is both mediation and interaction. And I think it's something like m1 minus m0 times y1. But so finally mediated, you can show that it is something like this. It's like the extent to which there is f of x on m multiplied by the extent to which there is an interaction between x and m and their effect on y. So really the total, so this is called a 3-way decomposition. I wasn't even going to mention this, but because you asked about it. The total causative effect can be decomposed into the pure direct effect plus the pure indirect effect plus this mediated interaction. What we usually do is we call this the direct effect, and this the indirect effect, which justifies why we call it the total natural indirect effect. You've got this option. Either you lump this mediated interaction in with a direct effect, in which case you're doing total sort of direct effect plus pure natural indirect effect, or lump this in with this indirect effect, and end up with a pure natural direct effect plus the total natural indirect. But it might seem odd what is total and pure. The pure sort of means without the mediated interaction, and total means with the mediated. Yes, a good point. So the effect, I guess it would be expectation of all. So you're saying the effect, so the extent to which drinking affects GDP, the increase in GDP due to drinking, divided by the to which drinking and GDP interact in their effect on growth. Although that isn't easy because this explanation is only really neat when M is binary and GDP is binary. But I think there is some equivalent way of thinking of the mediated interaction. But yes, it's sort of the extent of interaction multiplied by the extent of the effect of drinking on. I don't know if you feel for it than that. But I just certainly say that there is no thing to think of that as either direct or indirect. The thing is, if things are as nice and simple as those linear regressions, they're regression anyway. So if in the nice example where you can think of multiplying the coefficient, right, zero anyway, because this part is zero. Right. Divide them. They really pops up when things become messier, interactions and non-linearities. Yes. Was different, yes, because so things are non-collapsible. The lack of interaction on one scale implies an interaction on the other scale. Exactly, yes. So. Yes, so you think there is no nice interpretation when M is not binary. Okay, yes, you're probably right there. So the message so far is that this obsession with usually decomposing the effects into a direct and indirect effect, it's just not possible. When things are non-linear, there isn't a unique way of decomposing the effect into a direct plus an indirect. And, yeah, so we'll see when we go on to multiple mediators that things get even worse. But even two mediators, there's at least two, well, there's two ways of doing the decomposition. And there's getting away from that. You can't magic that away. Yes, just about, you may have noticed that I introduced the control direct effect, then used the natural direct and indirect effects, but I never said anything about a controlled indirect effect. And the controlled direct effect doesn't really lead to a sensible controlled indirect effect. You may well think, well, what because we have a definition of a controlled direct effect. So why don't we just define the controlled indirect effect to be the total correct minus the controlled effect at M? So you can do that. So there's nothing stopping you. This is well defined. This is well defined. So this is well defined. But the reason why this is not why I say it's not sensible is that this doesn't really match our intuition of what an indirect effect should look like. Because, and you can think of it easily as that, imagine you situation. So there is no effect of X on M, but S and M both affect Y. So what do you think the indirect effect intuitively should be if that's the situation? If there's of X on M, then I could have intuition would be no indirect effect. So any sensible definition of indirect effect should surely zero in this case. But as soon as you've got interaction between X and M, again, interaction is always the thing that spoils everything. So as soon as you've got interaction between X and M in the effect on Y, then this control direct effect depends on M. The total effect obviously doesn't. So if something that doesn't depend on M minus something that does depend on M, then you end up with something that does depend on M. So in this situation, this depends on M, i.e. it's not zero for all M. So that's why there isn't really a control in there. You see that already is that whenever we're talking about mediation, we're also talking about interaction. This lady pointed out, you know, as soon as you're in non-linear models and you're fitting a strict regression model for the outcome, then there is an interaction implied even if there is no interaction in that model. So I think what's clear is that the notions of mediation and interaction are intertwined. And so it's not surprising that Highlander Wheel's book on this topic has as its title, let me just find it quickly. The action in causal inference, methods for mediation and interaction. So, and interaction, they sort of go together. You can't separate, you can't discuss one without having to discuss the other. And have we reached? We've gone, I would say, more slowly than I was hoping. It's completely my fault. We've gone more than I was hoping until this point, but maybe it's good to have gone fully over the definition. So we now at least have I hope, careful understanding of what these actual definitions of direct and indirect effects are. Yes?
So, can you just start again, using the example, the control and the natural and what the differences are, but why do you not one versus the other?
Yeah. So the focus of the natural direct effect is that it has the indirect effect counterpart. So if you want to say, I want to decompose my total effect into direct plus an indirect effect, then already you are drawn towards the natural because you can't do that with the controls. But if you're only interested in direct effects, then how do you choose whether you're interested in the natural or the controls? I think it depends on the situation. So some people argued that the mediator is something that some nuisance, the controls makes more sense. So in some randomized experiments, it can sometimes be that being extra therapy means you stop adhering to your existing therapy. So then mediator. So it might find that this new therapy, or maybe different types of therapy. So I think one example that I've about is that when you have cognitive behavioral therapy, it can lead to better adherence, in fact, to antidepressive medication. So you might overall find that cognitive behavioral therapy has a beneficial effect on the outcome you're looking at. But the question might be, well, maybe that's just because it affects adherence to the medication. There, you could say that it would make sense to say, well, what is the control direct effect? So what's the effect of the cognitive behavioral therapy on the outcome in a hypothetical world where everybody adheres to their medication? So that's seeing everybody's M to 1 if M is adherence there. So I think it doesn't seem odd to imagine a world, even though it's impossible, I suppose, but it doesn't seem crazy to imagine a world where everybody adheres to their medication. When I start imagining worlds where everybody's systolic blood pressure is 120, that's an odd world to be thinking about. So I think when the M is some inherent part of the process, so you're interested in how this drug works. Well, does the drug work by lowering your cholesterol? And then, or by other means. And the question of by other means, you don't really want to imagine a world where everybody has a cholesterol of 3. That seems, so I think yes, I think often that is made. I do think you have to think in your particular example what makes more sense. I guess, so we haven't yet reached the point of discussing the assumptions under which these things can be identified. So the thing that may play the part when you're deciding which estimand to focus on, obviously the thing is which estimand is closely linked to your scientific question. But then you could say as well, it's needed to estimate, to identify the two things are actually different, and the assumptions for the natural direct effect are stronger than the assumptions you need for the controlled direct effect. So one would argue that sometimes if you think the assumptions for the natural direct effect are just too far-fetched, then you go for the controlled direct effect. But then it's a matter of, getting the answer to the wrong question versus the wrong answer to the right question, and all that sort of trade-off to be made.
In agriculture, I was approached by they test pesticides and herbicides and fertilizers, and they are very interested in separating the direct from the indirect effects. They want to know, that's how they learn. They didn't tell me a whole lot, because it was business secret, but I'm very interested in learning the different mechanisms by, for instance, fertilizer. So they really use mediation analysis for them. It's very interesting.
I guess they're in a situation where they can intervene on these mediators.
Yeah.
I guess sometimes they can.
That's exactly why they want.
Yeah. So they're in a better situation maybe than we often are as epidemiologists. Yeah, control direct effect. Exactly, yes. The control direct effect does match an experiment in a way, yes. A hypothetical experiment where you set M to that value for everybody, yeah. Yes, people would argue that that depends in a way what you mean by explaining mechanism. But I think really when people are talking about mechanisms, they want to know how important is this pathway versus another pathway. And as soon as you're saying that, then you're in the world of decomposition, and therefore you're in the world of natural effects. But examples that people sometimes like to think about is if you had a medication, so that caused a side effect, like say you take this medication for your anxiety, but effect of it is that it's called headache, and that headache itself might make you anxious. So you've got a choice between the control direct effect would be saying what's the effect of this medication on anxiety symptoms if we could set everybody's headache level 0. So that's imagining the eradication of headaches. That eradication of headaches, what's the effect of the medication on anxiety symptoms? But something that there never eradicates headaches. So maybe it's more natural to say the natural direct effect, which is the effect of the medication on anxiety symptoms. Everybody's headache level was what it would have been had they not taken the drug. So that's actually what that M0 is. So that's lying in a world where this medication doesn't cause headaches, what is for the medication on anxiety symptoms? And that sort of makes sense there, I think. So you still allow some people to have headaches, but they won't be headaches because of the medication. So that's simple, I think, that Judea Pearl uses to explain how he conceptualizes the natural directive. Yeah.
So implemented, like R, it would just, we'd be estimating the mediator effect as to Y out, given that exposure and all the other additional values. It's just like a G style notation, GX with an error term, so it's a conditional expectation of mediator.
It much depends what your model for Y is. So you, so if you're talking now about, you're talking about the direct effect.
Yeah, so it's generalization of notation for how you do it. I don't think it's
And so if we're going to estimate it by, so suppose we have C, which has some standards of X, and Y, let's say, diagram looks like that. Then what we're going to do is fit a model for Y given M, X, and C, or for M given C and X. And so you can write as the expectation of just on the first half, because obviously you could then do something similar for the second half. So if, let's say, you just want to write what's the expectation of this thing, it would be the expectation of Y given C equals this is the X equals 1, and then this is the C, M given X and 3, or given X equals 0, C equals 2, and then X. So this you could get from your regression of Y given C, X, M, but they're not precise predictions from that regression model, because they're predictions with X plus 1. This for M given X, C is generally to extract the density of that. Of course, depending on how simple this is as a function of M, it's well it's only the condition expectation that you need. But if you've got, so if the linear function of M, indeed you only have the expectation of M given X
with N, that's the deal.
That's very fair.
Yeah.
So let's we are doing for time. So do you break now, or should we go on another 10 minutes and have a break at 3? Yeah, okay, let's do that. So we've done a step of what are the S demands, and I agree that I haven't said anything yet, except in the last minute, about how we actually go and estimate those things. So the way we think about these things in causal inference is first write down what it is you want, then think about under what assumptions can you identify, and then you think about what estimation method you can then use. So first I'll just list the assumptions, and then I'll give you a little bit of an insight of the maths where you see those. So I give sort of, if you like, here, this is where we're going to end up, and then well, and then what assumption is this, which is a function only of the observed data distribution, is this equal to this thing with a counterfactual? And doing a little bit of that math, you will see intuitively why we need these different assumptions. Consider a setting with baseline confounders C, and so I've also included these intermediate confounders L. We're going to talk a lot about these. So C, these variables C are things that potentially could be common causes of X, M, and Y. So the economic status in our example could be something that affects your alcohol intake, it affects your GDT, it affects your systolic blood pressure. But there are some things, in our example, BMI, it's known to affect, or say adiposity probably. Adiposity changes your GDT, it changes your SB, but it's affected by how much you drink, rather than the other way around. So we do this distinction between the sort of baseline or background confounders that are not affected by X, and intermediate confounders that are affected by X, or at least potentially are affected by X. So sufficient assumptions under which these natural direct and indirect effects can be identified are first these technical assumptions of no interference and consistency. If done sort of traditional non-mediation causal inference, and you will have met these assumptions, no interference and consistency. I'm not going to go into them now. They're the sort of things that say that no interference is that the exposure of one person can't affect the outcome of another. You'll also need that the mediator of one person can't affect the outcome of another, and that the exposure of one person can't affect the mediator of another. All those sorts of things. Those are all no interference type assumptions. And then consistency assumptions are all these ones that say that when consistency for the simple case of one exposure effect on one aspect, it's the thing that says that one little x is equal to y and x is equal to x. So it's saying that potential outcome yx is actually equal to the actual outcome when the exposure level is that. Keep talking about what would SBP look like if you had been a drinker. Well, the fact is, if you were a drinker, then that is exactly what we see. So that's a consistency assumption that some argue is just definite common sense, and other people argue an assumption, and it sort of requires that you think of your hypothetical interventions sufficiently carefully for these things to be well defined. So we're not going to that now. So we have these sort of, let's call them the technical assumptions of no interference and consistency. Then we have usual sorts of no unmeasured confounding assumptions, which, so one advantage of the causal inference approach is that it gives a clear mathematical meaning to what we mean by unmeasured confounders. So they always look slightly horrible because they're conditional independent statements between mental outcomes and observed things. So, for example, for mediation analysis, we'll need that this potential outcome yx is independent of exposure x given the background confounders C. That same potential outcome is conditionally independent of the media M, given the background confounders, the exposure, and the intermediate confounders. But if you like this, then you can think of that as just saying there can't be any unmeasured common causes in the graph of X, Y, or unmeasured common causes in the graph of M and Y. Yeah.
Can you think of any practical
Oh, yes. So I think it's in infectious diseases are the main source of good examples of this, where let's say looking at the effect of a vaccine on measles vaccine, then if I'm vaccinated, then it will affect your probability of getting measles if you are in with me, if you see what I mean. So whenever you have an infectious disease, then preventing, doing something, giving the exposure to one person might therefore indirectly affect the outcome of another person. The sort of literature on no interference, or the literature on interference, is in some sense linked to the literature on mediation, because you end up estimating the effect on me of being vaccinated, and then the effect on you of the fact that I've been vaccinated. So there's a sort of an indirect effect for you by me, and a direct effect on me for the vaccine. Exactly. And so I think it's the sort of thing that if you do have data on who is connected to whom in the network, and then you can start modeling this, and you can do something about it. But, and then we'll also for the natural direct and indirect effect. So for the control direct, if this is actually enough, we just need no unmeasured confounding of X and Y and M and Y. But for the indirect effect, because it involves this M0, then we also unmeasured confounding of X and M. So we need that U3 not to be there. This, you could say, you would expect, right? Because we're talking about the causal. We know that if we want to estimate, I'm not talking about instrumental variables now. If we don't have instrumental variables, then to estimate the causal effect of something on something else, we need to assume that we've measured all the confounders of those two things. So not just talking about the effect of X on Y, we're talking about the effect X on Y that is mediated by M. Then it doesn't seem surprising that we need measured confounding assumption now 3 times for each pair, XM, MY, and XY. But actually, we might have that was probably enough with the no interference and the consistency assumption, that no unmeasured confounding assumptions on those would be enough to identify the effect. And to write these this expectation of potential outcomes in terms of the distribution of the observed data. But maybe surprisingly, these, although sufficient for the control direct effects, are not sufficient for the natural effects. We need something like this. So when I say we need something such as this, what is this assumption is sufficient, it's enough. It's enough slightly too much. We can do it slightly less, but we need something in addition. First assumption that was given, and that's most often given, is this cross-word independence assumption, that X star should be independent of YXM given C. So give the background confounders, M0, let's say, should be independent of Y1M. So the counterfactual, that's why I call it a cross-word independence assumption, because this is different from X star. So this involves saying that counterfactual in one hypothetical word is independent of counterfactual in another word. These background confounders, X, C. The strangest type. So certainly when you say this means in terms of this example. It's very difficult to say what this means in terms of the example, because it's really a difficult, these counterfactuals are already hypothetical. Now we're talking about, are these things independent across different worlds? But what is helpful to think about it is that you can know that this implies no, it's in fact stronger, but it implies no else. So, at this assumption, there can be no intermediate confounders. And you can probably why, because intermediate confounders would, because we're focusing on them there, would use a dependence between these two. So this world independence assumption that you always, you need something like it, either it or something less strong. You need something extra, and this is the obvious extra thing to say you need, and that extra assumption implies that you can't have any intermediate confounders, which is really a restriction, because in many examples, S and M may be far apart in time, so there's plenty of time for this X to cause something that goes on to confound the MY relationship. Yeah, no, it's not. It's not easy in fact. I think it's to do with how you. It's another sort of philosophical thing. It's about how you think about so it thinks like tells us that. So let's say you've got X, M, Y, and L. Let's not have C just to make things simple. Thinks of X as being some function of UX. So you've got these sort of independent error terms. UX affecting X, L affecting M, UM affecting M, and UY affecting Y. And the third thing about the word, if you like, is that S is equal to some function of UX, and you've got L, which is, so this is some other function. These are not densities now, they're just functions of L. This L is some other function of X and UL, and then M is another function of X, L, M, and Y is another function of X, L. But just that thinks that this is how the word he thinks that this structure, this thing called a structure, non-parametric structural equation model, it's a structural model, it's not a descriptive model. So it decides how these variables would be generated in any word. So meaning that if we intervene on X and set X to 1, so it's like setting X to 1 means you sort of abandon that part and set X to 1. When you set X to 1, it's FL of 1 and UL. And M1 is M of 1, L1 and UM. And Y1 is FY of 1, L1, M1, and U1. Now show that if the world follows this kind of structural model, so the limitation is not, so these functions can be anything. There's a limitation in using this to describe the world as it is. There is a limitation in putting a restriction on our model of the universe to say that you can generate any counterfactual using these functions. And so this is the non-parametric structural equation way of satisfaction is the fact that the form of this FM doesn't change from word to word. To show that if things follow this structure, then this independent fraction implies no L. And because you know this, if you write one FM and you write M X star, you simplify that kind of rule, you end up with a UL in both of them. They are associated because they're both functions of UL. So in other words, if the universe follows a non-parametric model, then this is equivalent to no L. The reason why it's stronger than no L is because you also have to assume this, because if you say, well, maybe the world doesn't follow. I'm just getting into the kind of philosophical aspects that I don't feel that confident about, but that's my understanding of why it's stronger than no L. But I think it's often written that it's the same as no L. And the sort of paradigm that there's no parametric structure equation model underlies the duration of everything in the world, then the two are the same. So I tend to think about it as the same. But he does, yes. But then I think somewhere in the paper there will always be a sentence saying, presume that the world can be described using a non-parametric structure equation model. So interested in this, I think Thomas Richardson is a person who's written a lot about, what are different forms of causal models. Because this is a sort of causal model. It's a way of, it's how counterfactual come about.
So an example there, and what and has another example there with x equals 0, that x equals 0, you're going to have between 0 and m1. And they're the same, what you're saying? Functional form in those two different populations.
Yeah, so M0 would be FM of 0, L0, and UN.
And it would have the same functional form.
We have exactly that FM does not change. Although, this test maybe isn't a problem because you create your FM of XL and UN to be equal to, let's say, X plus L plus UN plus XL plus SUN plus M plus XL UN. Whatever form you like, you can put an X in front of all the terms. You're not allowing the parametric form to be completely different in the X equals 0 and the X equals 1. But there's no restriction on what kind of function we can be. That is what's restrictive about it. I'm really on shaky ground now.
So the key is that the UN appears to be both L or X bar and then Y.
No, it's the UL that is the problem, because if YM will be SY of little x, L of little x, UY, and this thing will be SM of X star, of X star, and UN. If you write down what that is, LS X star will be something involving UL, and the X will be something involving UL. They'll both involve UL, and that's the problem. Sometimes the L is called a Wilhelmsian witness. The problems come about because you've got an LS here and an LS star here. So it's the witness that changes its story halfway through. Okay, I feel I'm not living by the interactive, the hands-on, what this session is supposed to be. I'm really sorry. So soon, I promise, we'll get on to the point where you start actually doing some analysis. We've said the cross-word independence assumption rules out intermediate confounders L. So maybe I should, in the interest of time, so he's saying there's in fact this weaker assumption instead that you can make that's nearly as strong but not quite, as described by Peterson. Basically the message is, they're all strong. The assumptions that you need for the natural effects are strong. So, as already said, if we can identify, I do a break. I think this is a good place to have a break. So we come back maybe in 15 minutes, so that and then go very quickly. Yeah, we're nearly at the point of starting the case study, so we spend the remaining time on that. Okay, so let's have a 15-minute break.
how would you? That's why I mentioned.
So carry on. What I always think it's worth when you're listing all the assumptions, things can be identified. It seems a bit of a pity not to show at least the steps of how you use those assumptions to do the identification, because I think it helps to convince people that these are not just things that somebody made up arbitrarily. So remember, if we can identify the first, so this thing in general, y, x, m star, obviously gives us both halves of the DE and the NIE, and by putting various ones and zeros in place of x and x star. So certainly if we can identify this, then that would be sufficient to identify the NDE and the NIE. And when I identify, I mean rewrite this as a function of the distribution of the observed data, so without these counterfactuals. Because that's all, the fundamental problem is that the thing that we're interested in involves a counterfactual. That's the only way of expressing it. How can we find an equivalence between that and something that doesn't involve counterfactuals, making assumptions? And then, so let's see how we can write this in terms of the only distribution of the observed data. So now, instead of densities I was using there, I will use probabilities. So this is in fact the relation if C and M were categorical. So see if any of those are continuous, then you need to replace the sums by integrals and the probabilities by density functions. But the is exactly the same. It's easier to think of them as if M and C were discrete. So first, the causal inference, we just write marginal expectation, a conditional expectation, given C and MX star, and then marginalize out over C and MX star. But because conditioning on X star equal to little m here, I'm able to rewrite the MX star here as little m. So that's really just rewriting this marginal expectation as a conditional expectation and then marginalizing out over the MX star and C. But cross-world independence assumption is this conditional expectation is equal to this conditional expectation, where I drop the conditioning on MX star equal to M. You see that conditional independence assumption helps us there. The cross-world assumption helps us. We can drop that conditioning on MX star equal to little m. And then by all those conditional exchangeability assumptions, well, the first lot, the first pair, allows us then conditional on C, because now we're in the world already where we assume there to be no L's because we've made the cross-world independence assumption. So now we have that YXM is independent of X given C and is independent of M given X and C. This conditional expression I can rewrite like this, inserting the X equal to X and the M equal to little m, changing anything. And likewise here, this conditional probability M star, C, I can rewrite with X equal to X star there, because X star, conditionally independent of X given C, was one of our conditional exchangeability assumptions. So these are no unmeasured confounding assumptions, and this is our cross-world independence assumption. But once we've done that, which I think I've rewritten here, now our consistency assumption, which among those for whom X is equal to little x and M is equal to m, YXM is equal to Y. And like among those with X equal to X star, MX star is equal to M. And then this, because we've rewritten even in terms of the distribution of the observed data. So do you see that it's nice to see where the different steps come in, the different assumptions come in, to convince us that these assumptions are relevant to achieving what we are trying to achieve. So then points us towards the most obvious, if you like, estimation method. So first of all, of course, by substituting the different values of x and x, we can find our expressions for the two effects. But just the most obvious thing is then to fit a model for y given x, m, and c, and a model for m given x and c, and then insert the probabilities and the expectations from those models into the right part of the equation, and then integrate out or sum out the m's and c. So there are lots of issues here. One of the traditional approach is to do with simple metric models, and then there are methods, extensions of those methods, like TMLE. There's a TMLE literature on direct and indirect effects, where they also end up with a sort of plain estimator of the expression, but where they can use machine methods so that we're not relying on simple parametric models for y given x, m, and c, and then given x and c. There are also parametric methods, that's double robust methods. There are many alternatives to this sort of simplistic, you could call it, approach of just plugging in some models there. But you see that the idea we're much better than we were to start with. Even if we are restricting ourselves to relatively simple parametric models, we can a logistic regression model for y given x, m, and c, for example, extract the expectation, and now we put that in, and we know sort of triangle, and we end up with a natural direct effect and a natural indirect effect. We can put interactions between x and m. We can put a term involving n squared. So this is much more general than that triangle we started off with, where we were just multiplying the coefficients. But one will argue that any reliance on a simplistic parametric model is not desirable. So these double robust approaches and then the TLE superlinear extents are all very nice things to do, but we don't have to go into all that. So today we'll focus on putting sort of relatively simple parametric models for these different components. So so far, mediation is not new, and everything is linear. Quite complicated structures, at least, could be incorporated using that very traditional approach, but it was unclear what exactly was being estimated, under what assumptions, and how things could be extended to non-linear settings. So the difference literature has addressed many of these, given ambiguous counterfactual definitions. That's what we've spent a lot of time talking about, that are independent of any model, and then deriving clear identification assumptions and flexible estimation methods. So the flexibility is much, much enhanced. Now we have these nice expressions for how to identify the direct and indirect effects from the observed data. But you could, the whole is still plagued by the strength of this cross-world assumption, and in particular, the fact that it rules out, or you could say most rules out, because of this caveat that assumption holds is sufficient. But it pretty much rules out how intermediate confounding, so these L's. So we're used to making assumptions about noise confounding, but now even if measured, these intermediate confounders are going to cause problems. And it's a taster of tomorrow that for the same reason that in general we can't accommodate L, then multiple mediators are also problematic. But this is another example where we have activity as a consequence of alcohol, then whether treating it as an intermediate confounder or as a separate mediator, we have difficulty. So we'll cover multiple mediator business tomorrow. Now we're just interested in it as a confounder, so we're only interested in decomposing the effect into that GDT and that via, not via DDT, but we still have the difficulty of this adiposity variable, or BMI, as we have it in the data set. And the suggested also that all this difficulty with the the intermediate confounder is overtension, yet another definition of direct and indirect effect, which is what's called the interventional effect. Because we have a lot of time, I don't want to spend a long time now. I want you to get onto the case study and actually doing some of this stuff. So I think very quickly, so this is in a way why I wanted to go through some of the maths of how you identify the effect from using the assumption. So the very first thing we did really was use the crossword assumption to drop this mx star equal to m from there. I think that the thinking behind the interventional effect is, well, we can't justify that assumption. We can't use this assumption. We can't drop that from there to reach here. But we're happy to make all the other assumptions. It's like we can reach here, but we can't make the additional steps to go back to here. So the interventional effect, and I think, well, what happens if we stop here? What if this becomes our target of estimation? So we then don't need to make the crossword assumption, because we're not even going to say to the estimating this top thing. Instead, our estimand is going to be what this corresponds to. That's the thinking of the interventional effect. And I'll put it a bit more clear now. So they're called randomized interventional analogues of the natural direct and indirect effects. But I just call it the interventional direct effect and the interventional indirect effect. So the interventional direct effect, the difference of two counterfactuals. Now, instead of saying it's now not a nested counterfactual, we're not saying y1 m0 minus y0 m0. Instead of 0, we're saying m star 0 given c, which is a random draw from the distribution of m among those with x equal to x conditional on c. So it's so in our example of the actual indirect effect as an interventional analogue is written like this. So you draw m from its distribution among the x equal to 1 group given c, and then change that to a draw from the distribution of m given 0, m given c in the x equal to 0 group, and then think about what would happen in the whole relation if you fit x to 1, change people's m from a draw from this distribution to a draw from that distribution. And in our example with the SBP, you could say that the interventional index effect is on the mean blood pressure of shifting the GGT distribution given confounded from seen in non-drinkers to that seen in drinkers, while affecting everyone with exposure to drinkers. We're no longer saying, if you think in terms of everybody in this room being in the population that we're using to define these effects, we're taking up everybody's blood pressure and the two conditions. Now, instead of shifting everyone to be addressed and then shifting everyone's mediator from what it would have been for them had they been a drinker to what it would have been for them had they not been a drinker, and everyone, we just take a random draw from that distribution in the drinkers versus in the non-drinkers. And that's sort of like, instead of shifting individual actual values, we're shifting the distribution in the room at large. And it's a conditional distribution given C, but not given L. So we're still allowed to have L. And so do you see my logic, that it's almost like saying, well, we can't make this first step, so not make it and start from here and say that this is the very thing we're going to estimate. Now, do we have, or this this with a 1 and a 0 minus this with a 0 and a 0 for the direct effect. Ask, well, do we have a meaning for that? Well, the meaning for that is as if we're measuring, it's as if we're estimating the effect of X on Y whilst drawing M from its distribution in non-drinkers given confounders. So that's sort of a way around this problem that we can't have L's. So we can't. So we if you have L's and we can't make the cross-word assumption, then one solution is to say that it's actually to estimate things in exactly how we would estimate them, but now to say that what we're actually estimating is the randomized interventional analogues of those indirect and direct effects. And so I guess that we now go straight on to also, maybe it's important to point out that one advantage is that when you add those two things together, you get the total causal effect, you get the internal analogue of the total causal effect, because now instead of saying let everyone's X to 1 and their M to M1, we're now drawing M from its distribution in the X equal to 1 group given C. So sort of there's a subtle difference between this and Y1 M1 minus Y0 M0. We are decomposing, but not the total effect, something that in the paper on this they called the overall effect, but it's really like a conventional analogue of the total effect. So I guess that we go straight now to the case study, because that's why we're here, and I've spent too long on numbers. Sorry about that. So the case study, so the data set, and you find it in the folder for the day one of this workshop, is pseudo-EGESC data. So I call it pseudo because of data restrictions. They are not the true data, but I've simulated them to be very similar to the EGESC data. So these are this data on. So the original study was a case control study looking at the effects of extreme alcohol consumption on mortality in a Russian town called Izhevsk. So it has a very high mortality among young men due to alcohol consumption. And actually, because we're interested in this mediation question of how much of the effect of alcohol and SBP can be explained by GGT, we'll actually look just at the population-based controls from that case control study. So we don't away the cases. We have just the population-based controls. And I've actually simulated the data. They're not the original data. So many simplifications. So these originally were exceptional in their richness of data collection on alcohol consumption. So I can't remember how many questions about alcohol consumption, how often they drank, what did they drink, how often they had this thing called poi, which is like a binge drinking episode in Russian. So there was a hugely detailed back to the questions about alcohol consumption. For the purpose of today, I've just a simple binary. Did they consume more 10 litres of ethanol in the previous year or not? So obviously that's a very simplistic thing to talk about a binary alcohol exposure when there's so more information, but it's just so that we have a simple thing to get our teeth into to start with. We have this alcohol consumption, either extreme alcohol consumption or not, if you like. And we have GT and SBP measured, and we also have age, socioeconomic status, which is just 3 categories, never X and current. In fact, in the data set we had cigarettes per day, but I've discarded that just to make things slightly simpler. Then, as I say, we've got this intermediate confounder, BMI. Also, there are no missing values in the data set that you got, which is actually the original data. So I can imagine, as everything is more complicated than we want it to be. So I try to make things so that we can just focus on the mediation issues and not all the other issues. But in India, of course, one has to think about all the issues together. Yeah, so are my suggestions. So hopefully you have access to the site as well, don't you? So you can, because I put up question 1 and 2 now, but at some point you'll go on to question 3 and 4, but you can go on your own time. So you find the data set in the folder, but also find some do files. So for each question there is a do file. And in the do file I suggest commands that one could use to answer the question. So because I know some of you may not be data users, and then it's frustrating then if you're struggling just because of the package. So I guess that especially if you're not familiar with data, then do files could be very helpful to you. And I think even, if I'll be here so you can ask me questions as you go along. And if there's something that I think it seems to be a common, then I'll try to talk about it to the group as a whole. But yes, also do use those do files because they might help you, especially when you get, I think, to the syntax for question 4 is quite difficult. So I would suggest that you do use the do file there rather than just trying to do it all from your own head. So I think that we spend now a little bit of time on this and then do a quick summary at the end. But
I just want to find the line.
wherever you have the data. That's a very good point. I think so. Yes, there'll be no problem. Problems, then maybe I can save the data. It's rejecting it because of the data being the wrong comma. Yes, you should. We use one command called paramed, but that's a small part of it. So you'll be able to do everything in R. And even the bit that we do in paramed, you can use mediation in R, I think, to do the same thing. So yes. saved a different version of the data with underscore V13. That should be, you'd be able to open that in version 13 of data. If it has uploaded.
On your code, you just simple regression. So you are linear. They are linear. You don't have any non-linear.
Not at the beginning, no. So
Means just the diagram.
yes, right at the beginning, yes, we just have everything as linear. So we're just doing the traditional at the beginning. Yeah, yeah.
But in that case, they don't have any of those problems. Because if you put everything linear, we don't have any of those computer fees. Because everything changes.
Yeah, so then,
Because if you linear, the only thing right now we're talking about is if we're doing regression.
yeah.
Linear.
So everything is linear then, I think all the problems go away. Although I think in theory to interpret things as a natural effect, you still need the cross-word assumption or something similar, which trivially, as long as the world follows a non-parametric statistical equation model. So I think that assumption you would still, but everything else, you're right, all the, yeah, and the controls is the same as natural, and everything is much simpler when everything is linear, yeah.
Right, on the diagram. You don't want to say. Right, and essentially response to, yeah, because this is, because if really matters, then really what it would say, there is something in there. I agree. Oh, here. Amazing, very right. Yeah. Right. Yeah, so are they on? And they all. I don't have. I think part of. He makes like a computer science and tries to build it up. When you look at it, really, any year, so you always assume that but they are really interested in the different ways. You might look into if that's your interest, you know,
Otherwise, it's all a bit mystical. But free to go for your cheese and wine. I'm not trying to you here.
Could you spend a time to explain one, like a weapon run,
Yes.
can you say, for example, why we do this coding? Say the full question.
So why do the what?
Like explain the code, like the program, the start program.
Yeah, question 4. Yes, so in fact, exactly the same request. Here, I was just checking that the two requests were the same. Yes. So there are many issues. So this is where we want to take into account the intermediate confounder.
Right.
So we're going to start with but it's sort of suggested that maybe we can do it step by step and actually not have L at first. But the aim is, and then we have, this is our structure. So we have this analytical expression that's got things. We know that our, let's say, the natural direct effect is equal to, and it's something, it involves the expectation of y in b x l. So it's here it will have a similar expression with x equals to 0, and then we integrating this over some density that involves m given maybe a value of x and other value of l, and then we have a density involving some similar, and then we have a density of l given x and c, and we have density of b. We'll integrate all of this over c, l, and s. And for still models, you usually write these things out and what the direct effect is of the parameters in the model. So if you think the SIMPOD implement a coefficient of C, a coefficient of X, a coefficient of M, a coefficient of L, and like all the way down, then if things are relatively simple, you end up with stabilistic expressions. So things like then the directive F is equal to, I'm sort of just making that thing up now, with mu X times mu sort of, you know, where this is the coefficient of X in the first model, this is the coefficient of, or let's say, you know, this is the coefficient of X in the other model. You end up with sort of a more complicated version of that simple sort of times that we started off with.
They have those linear, if everything's linear, so we just say, the parameters come together, some get you times together, right? So if everything's linear, right now, of course, you assume a linear answer. If it's linear, that A, B, E will be just some parameter combination.
If everything is linear, then actually we know that if this
Yeah, you have a parameter.
coefficient is alpha,
Yeah.
and this coefficient is
Beta.
beta,
So,
and actually this coefficient is,
yeah,
then the
so
natural
we just time
directive
together.
outlet beta
Yeah,
gamma, for example,
yeah.
is the directive. So indeed, if everything is linear, then this mesh starts to something very easy. The more complicated this gets, the more complicated this gets, and the point where this becomes intractable. And so that's why, as things get more complicated, it becomes useful, instead of trying to do this, and also there's features that you have to do this afresh each time. If you say, okay, now I'm going to add an XL interaction in CIMPOD, okay, then we have to go through the algebra again. But if you avoid doing that fresh algebra each time, and indeed as the models get more complicated, the algebra is just impossible, then there's a sort of single technique that can work no matter how complicated the models are, and that is this idea of simulating, so doing bimodal power simulation. The idea is that if you want, suppose you, so we're interested in, let's say, the natural directive. So the expectation of y1 0 minus expectation of y focus first on the first part. So let's say we're interested in this part, and then we will do something else on that part. So we want to estimate this thing. And our strategy is going to be, so we've got C, X, L, M, and Y. So our sequence, we can leave C as it is. We're going to set X to 1. And we'll regress L on C and X. And we're going to use that model to predict L1. That we draw from this distribution of L given C and X, with X set to 1 and C as it is. And then we're going to regress N on C, X, and L. And we'll use that to draw N0. So N0 will be what we get when we draw from this distribution with X set to 0 and X set to L0. So in fact, when we are at this point, we need to draw a 0 as well. Then we'll set L to L0, X to 0, and that will allow us to get N0. And so then finally, we will get Y on C, X, L, and M. And that to draw Y1, M0. How will we do that? We'll set X, just leave C as it is, set X to 1, set L to L1, and set M to M0. And draw from that. So then we end up with a sort of a draw each person of these 1 M0 and average them all over the people we've got, and then give us an estimate of that. So that is the idea of using Monte Carlo simulation. So that's all really going on here. So you've got these sequence of models. So even if we go to the most complicated one, we'll have L for L first, then we draw L1 and L0. You see draws because we're adding random nodes at the end. With ERMSE is where data stores its estimate of the root mean square, which is the estimate of sigma, the standard deviation of the residual error. Here we fit our model for M given L, X, and the C's, and we draw M1 and M0. You see, we set L to L1 there and set L to L0 there. And then finally, when we draw Y1, M1, Y1, M0, and Y0, M0, exactly as I was saying there, M to M1 there, to M0 there, to M0 there, L1, L1, L0, and then the point have this coefficient of alcohol here because these are the ones where we set X to 1. We do that here because we're setting X to 0. That's all I'm doing. The extra complication comes in places. First, actually we want to minimize the Monte Carlo error. And so instead of just doing this for each person in the data, we for 1,000 times more people than that. And that means that at first, we should create 1,000 copies of our data set. Except every time we do the regression, we need going on the original data. Otherwise, we'll end up with the wrong standard deviation of going these things. So I started off expanding the data set to 1,000 times the size. But the time I do a model, it's if duplicate equals 0, and that's this value that the expand command generates. So I say if you're a member of the original data set, then fit this regression. But then when I predict L and draw the L1s, L0s, and the M1s and M0s, I'm drawing those for everyone. So I'm drawing always 1,000 times more the size of my data set. This means that at the end, when I'm calculating my estimates, I've got less error that's just due to this. So I'm closer and closer to what it would have been if I'd done analytically. And when you do it for this first example, which is just exactly the same as our first traditional analysis, you do almost exactly the same parameter. And the second complication is that for inference, we're going to use the bootstrap. So write the whole thing within a program, then we extract these things from the program, and we use the bootstrap to back that. So the kind of ingredients. And then, of course, we can put interactions, like here, as an interaction between the user and the mediator. That's actually the only nonlinear thing in the whole thing, but I'd be much more nonlinear. So if this were a bad outcome, I could have logistic here, and could have interactions all over the place, and I could put log BMI squared, log GGT squared. It would just mean that then I need to put N1 squared here. And so there's no end to the complexity of the models that you can fit once you do it this way. It's just worth knowing that it's nicer to be analytic if you can, but if things get too complicated, it's nicer there is one way that, it's a little bit cumbersome, but it will always get you there. And there's actually a data command that does all this called gformula. But I decided that it was probably better to see the steps that gformula does, and also gformula is very slow. So in any practical example of any resized data set, it's probably better to write your own formula anyway.
I'll give him the gformula using more like simulation based, right?
Yeah. So,
you simulate to get those details.
Yeah.
The gformula is really like a numerical integration.
Yeah. But the formula in data has a mediation option. So then it's not technically G formula, it's like a slight mediation adaptation of G formula. But it's exactly this. It just, but it's so only because the data management part is slow, not because of not because it's doing anything any different from this. So there's no difference. The only difference is that in the randomized interventional analogues, that's where I had an L to simulate. And so then I know that I can't possibly be estimating natural effects because of an L, and therefore the crossword assumption cannot hold. It's because the Peterson assumption does hold here, because we have or it holds at least, because we do have an L that's a model here. Effects of L are completely linear. I don't think I have any XL interaction or an L squared or anything like that, or an LM. So in fact, then the thing could, under the if the Peterson assumption holds, they could actually be estimating natural direct and indirect effects. It's just I always feel that in general, once there is an L, I tend to think, well, I'm not estimating natural effects anymore. I'm estimating randomized interventional effects. This caveat, very small gray in between, where in fact that's not the case, and the example actually does fit into that gray area. But so where the crossword assumption does hold, or the Peterson assumption does hold, the natural and the intervention analogues are the same anyway. So what you could always call everything intervention analogues, and that'd be wrong. It's just that under this assumption, there are actually also natural effects. So that's why it's not logical, but that's why in the first two, I did call them natural, because there's no L, so there's like a chance that they are natural if the crossword assumption holds. But in the third example, because I had an L, I was thinking, well, I definitely am not doing natural anymore, I'm doing interventional analogues. But in fact, because I was using only linear involving L, and all the models were linear regression models, then in fact, there's still a chance that those are natural effects, because the assumption has a chance to hold. That's a good question, and you're absolutely right. So here, you'll notice that we never draw an M1L0 or an M0L1. We only draw M1 and M0. So when I draw M, I set, sorry, I'm looking at the wrong place. When drawing M1, L is set to L1. And when I'm drawing M0, L is set to L0. So that means that this whole part should be, if those are correct, this should be equivalent to dropping L from here, so doing this, and drawing the L part here, and drawing the L part there. Actually give me the same, on average the same, you know, the exact same estimates at the end. So the only reason, so you would argue, the only reason I did this is because, yeah, actually, you're right. It is, if this model holds, then this model holds. But model hold without this model holding. So this is more robust. So this is probably more robust. This gains you a little bit of precision, because you're including L in model for M. If you do that correctly, you will gain a little bit in terms of precision. but like that you're paying a price in terms of I'm now making an assumption that that log GT depends linearly on log BMI. If that's wrong, then I might be better off in terms of bias with the second. Yeah, this is I think why in the end everybody.
In the model for the error. Right, so if L does something funny, the combination of the error from L and error and error dropping the L, then you're responding to error.
Right. Yeah. Yes. So, but you're right. Yes. So the assumption that the error is normal could hold here and not there, or vice versa. Yeah. In theory, you should look at all that, and that's why I think eventually we'll all probably be doing machine learning for these, because these are the bits that really it's crazy that we're not using the power of the machine for parts. The machine learning eventually will be so that do all this, but with cross-validation so that it's not overfitting anything, and you'll always be better than what we can do without it.
So whenever I think about regression-based simulation methods, what strikes me is that we are drawing in each potential world an error for each variable. And thinking practically, there might be, a lot of things that are quite the same. That may be the same across the world. Error of M1 and error of M0 should be correlated.
The point here is that doesn't matter, because if the cross-world assumption holds and you're estimating natural effects, or the cross-world assumption doesn't hold and you're not estimating natural effects, the whole point is that you're never using the correlation between M1 and M0. That's the identification step, such that correlation should never enter the final estimate, even though it looks like I've drawn them independently here, but I could have drawn them. In fact, probably I would use my Monte Carlo error if I think it could go either way.
I try to simulate it where I don't let them correlate, and where I let them correlate on 5 or something. And in one situation, I find that both ways are unbiased, but one has less variance.
I can believe that. Yes, yeah. I think you're absolutely. So I totally agree that it will impact the variance, but it shouldn't impact the estimate itself. That's under the assumptions we're making. That's the whole point almost. That that cross-world correlations of all types don't enter into the final for the estimate. But that. Then yes, there is but that's because the effects then are not identified. We never know that. There's no information in the data, remember, about that cross-world correlation. And so it's true that then if you have an effect that is not identified precisely because it is a function of that cross-world correlation, then the only thing you can do is some sensitivity analysis where you pick a value for it. Yeah. Yes, exactly. Yeah. Maybe see some of you tomorrow for the second workshop. You'll see